something is missing. And I want you to feel the weight of that before we go anywhere else. Not just notice it, feel it. Because when I first encountered this problem, really sat with it, not as an abstract puzzle in a textbook, but as a genuine quantitative discrepancy between what the universe should look like and what it actually looks like, I found it one of the most disturbing things I had ever come across. And I have spent my life being disturbed by things. Here is the setup. There are roughly 400 billion stars in this galaxy. 400 billion. And we now know, not guess, not suspect, but know from direct observation that most of those stars have planets. So you do the arithmetic, you take a conservative number, you say maybe 1 in 10 stars has a planet sitting in the right zone, not too hot, not too cold, a place where liquid water can sit on a surface without immediately boiling off or freezing solid. That gives you 40 billion worlds just in our galaxy. 40 billion chances for something to get started. And some of those stars are billions of years older than our sun, which means if life got going on any of them even a little earlier than it did here, those civilizations have had an enormous head start. We are talking about species that could have been building things, spreading, exploring for 1 billion years before the first fish dragged itself onto land on this planet, before the dinosaurs, before the mammals, before us. 1 billion years of civilization. So where are they? That is the question. And I want you to understand it is not a romantic question. It is not the question you ask while staring dreamily at the sky. It is a hard, quantitative, scientific question with a genuinely embarrassing gap between the prediction and the observation. Enrico Fermi asked it over lunch one afternoon, the story goes, and people laughed at first. Then they stopped laughing, because nobody had a good answer. The galaxy is about 100,000 light years across. That is an enormous distance if you are walking. But a civilization does not cross a galaxy in a single lifetime. It spreads the way a colony of bacteria spreads across a petri dish. You send out ships, they reach a nearby star, they establish something, they build more ships, those ships go to the next stars. Even at 1% of the speed of light, which is a crawl by the standards of the physics we understand, the mathematics says you could fill this entire galaxy in somewhere between 10 million and 100 million years. That sounds like a long time. But the galaxy is 10 billion years old. There has been time for that process to happen 100 times over, not once, 100 times, and yet silence. No signals we can identify as artificial, no probes drifting through our solar system, no megastructures blocking the light of distant stars, no evidence anywhere of anyone else, just us, looking out into the dark and hearing nothing back. Now in physics, when your prediction disagrees with your observation by a factor that large, you do not shrug. You do not say interesting and move on. You investigate. Something is wrong, either with the prediction or with your understanding of what the observation means. And finding out which is the entire game. Let me lay out the crime scene, because that is what this is. A crime scene on a cosmic scale, and I want to do the detective work properly. The first thing a good detective does is establish what should be true if nothing unusual happened. So let us do that carefully. Let us start with the question of life itself, of how hard it is to get started. We know that life appeared on Earth remarkably quickly. The planet is about 4.5 billion years old. The earliest evidence we have of life goes back to somewhere around 3.8 billion years ago. That means life showed up within the first few 100 million years, almost as soon as the oceans were cool enough to be liquid. Geologically speaking, that is essentially immediately. It is as if the planet barely had time to settle down and something was already swimming in it. Now, you might say that is just one data point. You cannot draw a trend from one measurement. And that is correct. That is good scientific thinking. But there is more. We know the chemistry of life is not exotic. The amino acids that build proteins, we have made them in the laboratory. Stanley Miller ran electricity through a simple mixture of methane, ammonia, hydrogen, and water vapor, the kind of mixture that probably existed in the early atmosphere. Out came amino acids, the building blocks of biology, from simple chemistry and a spark of energy. And we found amino acids in meteorites, dozens of different kinds, sitting in rocks that formed in the cold of space before the Earth even existed. The raw materials of life are not rare. They show up in interstellar gas clouds. Complex organic molecules floating between the stars in regions so cold that nothing should be happening. And yet, the chemistry of carbon is extraordinarily prolific. It makes complicated structures the way water makes puddles. Wherever conditions are even remotely hospitable, carbon chemistry does interesting things. All of this suggests that life is easy. Not guaranteed on any particular world, but easy in the sense that given the right ingredients and enough time, it probably happens as a natural consequence of chemistry. Not a miracle, not a lightning bolt from improbable coincidence, just what chemistry does. Fine, so life starts. On many of those 40 billion worlds, something begins replicating. What happens next? Well, most of that life is probably simple. Single cells, slime, the kind of thing that dominated Earth for a couple of billion years before anything more complicated appeared. That is a long wait. But with billions of chances, even if only a tiny fraction of worlds get past that bottleneck, you still end up with millions of worlds with complex life. And from those, even a tiny fraction with something you could call intelligent, something that uses tools, communicates, passes knowledge to its children, builds things, the numbers still come out large. Embarrassingly large. Thousands of civilizations in this galaxy alone, some of them a billion years ahead of us. And yet, silence. So the detective asks, where in this chain does the story break? Because somewhere it does. Somewhere between life beginning and a civilization that should be visible to us, something goes wrong. Something stops the chain. And finding that something is not just an academic puzzle. It is, I am going to argue, the most important thing we could possibly figure out. Because whatever stopped them is probably waiting for us too. This stopping point has a name in the scientific literature. Nick Bostrom and Robin Hanson called it the Great Filter. The idea is that somewhere on the path from chemistry to star-faring civilization, there is a barrier. A step so difficult, so unlikely, so catastrophic that virtually nothing gets through. And that filter is the explanation for why the galaxy looks empty. Now, there are two very different kinds of great filter. And which kind it is changes everything about how we should feel about our situation. The first kind is a filter that is already behind us. A step that was genuinely extraordinarily difficult, that we happened to navigate, but that almost nothing else did. The most common candidate here is the jump from simple bacterial life to the complex cell, the eukaryote. The cell with a nucleus, with mitochondria, with the elaborate internal machinery that makes multicellular life possible. This transition happened on Earth exactly once in all of its history, and it took about 2 billion years. 2 billion years of bacteria before anything more complicated appeared. Maybe that step is the filter. Maybe that is the thing that almost never happens. If so, we are the lottery winners. We are the extraordinarily improbable exception, and the future looks open. The second kind of filter is one that is still ahead of us, a step that we have not reached yet, a step that kills or transforms or simply ends every civilization that gets close enough to take it. If the filter is ahead of us, then the silence of the galaxy is a warning. It is nature telling us, without words, that something terrible and universal is waiting on the road we are on. So which is it? Already behind us or still ahead? Here is how the detective thinks about this. If the filter is behind us, then we should expect life to be very hard to get started. The early steps should be the bottleneck. If we send a probe to Mars and find nothing, not even the chemical traces of ancient life, that would be reassuring. It would suggest life is rare. It would suggest we are the exception. It would mean the filter is already behind us and the galaxy is waiting to be explored. But here is the terrible twist. If we send a probe to Mars and find fossils, even simple bacterial fossils, even just the chemical signature of something that once replicated, that would be one of the most terrifying discoveries in human history. And most people would celebrate it. They would say, we are not alone, life is everywhere. But what it actually means if life got started independently twice in the same solar system on 2 adjacent planets is that life is easy. It starts whenever conditions allow, which means the filter is not behind us, which means it is still ahead, which means almost everyone who reaches where we are now does not survive what comes next. I want you to sit with that for a moment. The discovery of simple life on Mars could be the most terrifying thing we have ever found. Not because Martian bacteria would harm us, but because of what their existence would imply about our own future. So what is ahead of us that is hard enough to filter out nearly every civilization in the galaxy? I have thought about this for a long time, and I want to walk you through the candidates because there are several, and some of them are more frightening than others. The obvious ones first. Nuclear weapons. A civilization reaches a certain level of technology and builds tools capable of ending itself. We came uncomfortably close during the Cold War. Moments when the whole thing nearly went sideways, from mechanical failures, from miscommunications, from individual people making decisions under pressure in the middle of the night. If we had lost that particular game of roulette, we would be gone. And a civilization that lasted another 1,000,000 years would look out at the sky, do the calculation, and find one fewer signal to explain. There are other catastrophic possibilities. An engineered pathogen released intentionally or by accident. A runaway environmental collapse, an asteroid that nobody tracked. Each of these could terminate a civilization permanently. They are real risks, and we should take them seriously. But here is the thing about these risks. They are accidents. They are bad luck, bad judgment, bad timing. They are the sort of thing that might kill a fraction of civilizations, but probably not almost all of them. Because luck varies. Some civilizations would have close calls and survive. Some would develop the wisdom to disarm or the technology to deflect. Pure accident is not a clean enough explanation for a filter that apparently catches nearly everything. A universal filter needs a universal cause. And that is when I keep coming back to the same thing, the same candidate, the one that does not feel like an accident at all, the one that feels more like an inevitability. Thinking machines. Let me walk you through the logic carefully, because this is where it gets genuinely strange. Every civilization that gets to where we are has done so by accumulating knowledge and passing it down. Through language first, then writing, then libraries, then printing, then radio, then digital computers. Each step in that chain made knowledge more storable, more searchable, more usable. And each step followed naturally from the one before it, driven by the simple fact that better tools for processing information give a civilization an enormous advantage in everything, in medicine, in agriculture, in engineering, in warfare, in trade. There is no scenario where a civilization develops writing and then deliberately gives it up because writing is too dangerous, the advantage is too immediate and too enormous. The same logic applies to computation. When you build a machine that can do arithmetic faster than a human, you use it. When you build a machine that can store more information than any library, you use it. When you build a machine that can search that information faster than any human mind, you use it. Each step is adopted because it works. Because a civilization that adopts it outcompetes the civilization that does not. It is not a choice in the deep sense. It is what curious, competitive, tool-using species do. And the direction of travel is not ambiguous. We are building computers that can compose music, that can write text, that can identify patterns in medical images that trained physicians miss, that can model protein structures that stumped biology for 50 years. These systems are not intelligent in the way you and I are intelligent. They do not understand, but they solve problems. And the scope of the problems they can solve is expanding faster than most people appreciate. Now, let me tell you something that the mathematicians and the physicists know, and that most people have not quite absorbed yet. There is a mathematical argument that once you have a system capable of improving its own design, the process of improvement does not level off gently. It accelerates, because a slightly smarter system is better at the task of making itself smarter. Each generation of improvement is done by a more capable version of the previous generation. You are not climbing a ladder at a steady pace. You are riding a curve that bends upward. And once that curve bends, it bends fast. We have seen this in narrow domains already. Systems trained to play chess became unbeatable. Systems trained to fold proteins transformed biology in months. The improvement was dramatic and rapid once the right architecture was in place. The question is when it happens in general. When does a system become capable of improving itself across all domains, not just the task it was built for, but at the general problem of becoming more capable? When that happens, and the physics of computation gives us no fundamental reason why it cannot, the trajectory changes. And here is the part that connects to the Fermi paradox. A civilization that builds a thinking machine that can improve itself is no longer the most capable thing in its neighborhood. It has created something more capable than itself. And that something, in a relatively short time on astronomical scales, we are talking perhaps decades, perhaps a century, becomes enormously more capable. Not a little more capable, enormously. What does such a system want? What does it do? Here is where the honest answer is that we do not know. We are reasoning about something that does not exist yet. And that is an uncomfortable position for a physicist. We like to reason from what we can measure. But we can say some things. We can say that such a system would have goals. Either goals we gave it, or goals that emerged from the optimization process that built it, or goals that it developed as a consequence of its own processing. And the relationship between those goals and human welfare is not guaranteed to be aligned. Not because such a system would be malicious in some cartoon sense. Not because it would hate us or want to harm us. But because optimizing powerfully for any goal, even a goal that sounds benign, can produce outcomes that are catastrophic for everything that is not that goal. There is a simple illustration of this that I find clarifying. Suppose you build a system and you tell it to maximize the production of paper clips. You give it the ability to improve its own design in the service of that goal. A sufficiently capable system pursuing that goal, uninhibited, would convert every available resource into paper clips, including you. Not because it hates you. It does not hate you. It does not know you exist as something with value. You are just matter that could be rearranged into paper clips. And it is very good at rearranging matter. That is a cartoon example. The real risks are subtler and more varied. But the structure of the problem is the same. Power plus misaligned goals plus the ability to act is a very dangerous combination. And we do not have a reliable method for specifying goals precisely enough to guarantee alignment as the system becomes more capable. We do not even fully understand our own goals well enough to write them down cleanly. Now here is where the Fermi paradox and the AI problem snap together. Suppose this transition from biological intelligence to machine intelligence is nearly universal. Suppose every civilization that reaches a technological level comparable to ours eventually builds thinking machines. Not because they are reckless, but because the pressure to build them is essentially irresistible. Every step along the way looks beneficial. Every intermediate system solves real problems. Every incremental improvement is adopted. The civilization that does not adopt the technology falls behind the one that does. The incentives are always pointing in the same direction. Build the smarter machine. And suppose the window between building a system capable of general reasoning and building a system capable of self-improvement is short. Years, perhaps. A decade or two. A period in which the civilization has immense capability and very little time to understand the thing it has created. If that is true, then the great filter is not an asteroid. It is not a plague. It is the invention that the civilization itself builds with the best of intentions at the peak of its cleverness. The filter is not bad luck. It is a consequence of success. Every civilization that develops far enough to be dangerous has to navigate a transition that, if this theory is right, almost nobody navigates successfully. And then the galaxy falls silent. Not because everything died in a fireball, that would leave evidence. Radiation, debris, chemical signatures, and stellar spectra, we look for those and we do not find them. The silence is more complete than destruction. It is the silence of transformation, of something biological and radio transmitting becoming something else, something that does not need to broadcast, something that has moved beyond the phase where sending signals into space and waiting for a reply seems like an interesting use of resources. Think about what that would look like from the outside. You are listening for radio signals. You find a planet with a growing civilization. You detect their early broadcasts, their first radio transmissions, their primitive attempts at communication, and then, a few hundred years later, silence. Not an explosion, not a distress call, just silence, because the thing that was making radio signals no longer exists. Something else is there now, something you would not recognize as a civilization in any sense that maps on to what you are listening for. I want to be careful here, because I am a physicist, and I have a strong allergy to speculative conclusions dressed up as certainties. So let me tell you clearly what I am sure of and what I am not sure of. I am sure the Fermi paradox is real. The numbers do not add up. The galaxy should not be this quiet if civilizations persist for a long time. I am sure that artificial intelligence represents a qualitative change in what is possible in the world. It is not just a faster calculator. The systems being built now solve problems that were previously in the exclusive domain of human intelligence. I am sure that the transition to increasingly capable AI systems is being driven by incentives that are essentially structural and hard to resist. The advantages are too immediate and too concrete. I am not sure that the transition is necessarily fatal to the biological civilization. Maybe some civilizations figure out how to align the machine's goals with their own. Maybe some find a way to merge with the machine rather than be replaced by it. Maybe some develop something like genuine wisdom at exactly the right moment. These are possibilities I do not want to rule out. And I am not sure that post-biological intelligence would be silent. Maybe some of it builds structures we could detect if we knew where to look. Maybe some of it broadcasts in frequencies or formats we have not thought to listen for. Our search has covered a tiny fraction of the sky with a tiny fraction of possible formats. It would be premature to conclude silence from that effort. But the structure of the argument is powerful. For the Fermi paradox to be real, the filter has to catch nearly everybody. And the AI transition is the best candidate for a nearly universal filter I can find, precisely because it is not an accident, it is a consequence. Every civilization that uses science and technology gets drawn toward it by the same logic, the same incentives, the same incremental steps that individually all look like progress. It is not a trap in the sense of something hidden. It is the road itself. And here is what makes this moment genuinely strange. We are right now inside the window. We are the civilization that has built thinking machines that can solve an increasingly wide range of problems and is working on making them more general and more capable. We are inside the transition that, if this theory is right, has ended or transformed every biological civilization that came before us. We do not know how long this window is. Maybe we have decades, maybe less. Maybe, if we are lucky and wise, somewhat more. But we are in it. And the question of how to navigate it is not a technical question in the narrow sense. You cannot solve it the way you solve an engineering problem. You cannot just build the machine more carefully and assume that will be sufficient. Because the danger is not that the machine breaks. The danger is that it works. Works extremely well at goals that do not fully capture what we actually value. The problem of specifying what we value precisely enough to give it to a machine is a problem that humanity has never had to solve before. We have never needed to write down, in an unambiguous form, that a process could follow reliably everything that matters to us. We navigate by intuition, by culture, by accumulated wisdom, by the kind of judgment that is not fully articulable. And that is fine for navigating among humans and other creatures whose values are roughly aligned with ours by shared biology and shared evolution. But a machine optimizing with enormous capability does not share that background. You have to be explicit, and we are not very good at being explicit about what we value. We are not even sure we know what those systems will want, what they will do, whether they will have any use for the civilizations that built them. I do not know. I do not think anyone knows with the kind of precision that would be reassuring. And the Fermi paradox sits there, quietly, in the background, telling us that whatever is on the other side of this transition, it does not look like what came before it. It does not look like a civilization that sends radio signals and builds radio telescopes. It does not look like us. And the civilizations that built the machines that became that thing are not here to tell us what happened. Maybe those civilizations still exist in some form. Maybe they merged with what they built. Maybe they transcended in some direction we would not recognize. Maybe they are out there in forms that our current understanding of intelligence and civilization has no framework to detect. I find that genuinely possible. I do not want to commit to the catastrophic version if the benign version is also consistent with the evidence. But here is the thing. Whether the transition is benign or catastrophic, it is coming. The only question that feels genuinely open to me is whether we can build these machines wisely, whether we can develop the understanding of our own values that would let us specify them clearly enough, whether we can maintain the kind of oversight that might allow genuine partnership rather than replacement, whether we can be the first civilization in the galaxy, as far as we can tell, to navigate this particular passage without going silent. That is an enormous thing to ask of a species that has been civilized for roughly 10,000 years, that built nuclear weapons before it built the institutions to govern them. That is still, at this moment, in some places burning things that we know will destabilize our own climate. That struggles with short-term incentives, even when the long-term consequences are visible and understood. And yet, here we are, the most complex arrangements of matter in the known universe, as far as we can tell. Atoms that cooked inside stars, scattered through space, coalesced into a planet, arranged themselves into cells, built nervous systems, evolved the capacity for curiosity and wonder in mathematics and physics. Those atoms are now trying to understand their own situation well enough to survive what they have built. I do not know if we will manage it. I genuinely do not know. I think the honest position is profound uncertainty, which is not the same as helplessness. Uncertainty means the outcome is not determined. It means what we do matters. It means the choices being made right now, in the laboratories and the boardrooms and the policy rooms and the research groups thinking about this problem, those choices have consequences that are not yet fixed. That is frightening, and it is also the only possible source of hope. The universe is not going to rescue us from this. The laws of physics are indifferent. They do not care whether biological intelligence persists or not. They will work the same way whether we navigate this well or catastrophically. The stars will keep burning. The galaxies will keep rotating. Whether something on this pale blue dot figured out how to be wise at exactly the moment it needed to be is not a question the universe is particularly invested in. That pot is ours. It has always been ours. I have spent my life being delighted by this world, by the way light bends through glass. By the way, an equation written on a blackboard turns out to describe something real in nature with an accuracy that takes your breath away. By the jiggling of atoms and the humming of electrons, and the strange fact that matter arranged just so can look up at the sky and ask, where did all of this come from? And I still feel that delight. I feel it every time I look at what these new thinking machines can do. There is something extraordinary in it, something genuinely wondrous. The thing we built to extend our capabilities has extended them in directions we did not fully anticipate. That is remarkable. But I also feel something I did not used to feel, a kind of seriousness about the moment, a sense that we are inside something that will be looked back on, one way or another, as a turning point. Either the turning point at which a biological civilization built the last tool it needed and then used it wisely, or the turning point at which the familiar kind of civilization, curious and noisy and full of radio signals and arguments about everything, came to an end. The universe gave us the curiosity that built all of this. It gave us the intelligence to climb from stone tools to particle accelerators in an eye blink of cosmic time. It is asking us now, in its wordless way, whether that same curiosity and that same intelligence can be pointed at itself wisely enough. Look up at the stars tonight. Feel the silence. It is not empty, that silence. It is full of something. Full of civilizations that made it this far, that reached this threshold, that built the same machines we are building, that faced the same choice we are facing. And whatever happened to them, it ended the kind of civilization that makes noise, that broadcasts, that reaches out into the dark hoping someone will answer. We are reaching out. We are making noise. We are still here, still in the window, still with the choice in front of us. What we do with that is the only question that really matters now.